Look around the room right now. What do you actually see? You probably noticed the device you were listening on, the walls around you, maybe a cup of coffee on the table. You experience all of this in three very familiar dimensions of space. You have length, width, and height.
And if you want to get technical and add the flow of time into the mix, we are navigating a four-dimensional reality. For centuries, humanity just accepted that this was the complete map of existence. We thought our eyes and our basic physics gave us the whole picture of the universe.
But according to modern theoretical physics, we are essentially walking around blindfolded. The mathematics of string theory suggests that our universe doesn't just have four dimensions, it actually has 10.
It sounds like pure science fiction, doesn't it? 6 extra dimensions of space, just hiding out of sight? They are folded up so tightly and so microscopically that they are completely invisible to our most powerful microscopes.
And that is exactly what we are diving into today. Because these hidden dimensions aren't just passive, empty spaces. They are actively controlling our world. They dictate the fundamental rules of reality. We are going to break down this mind-bending cosmic geometry, figure out if information is secretly passing between their world and ours, and uncover 3 hidden forces shaping absolutely everything we know.
It is a massive topic. To even begin wrapping our heads around it, we have to answer the most obvious question first. If there are 6 extra dimensions of space, where exactly are they? Why can't we wave our hands through them?
I think the best way to visualize this is to step away from the abstract math for a second and picture a simple garden hose stretched out across a massive lawn. If you are standing a mile away and looking at that hose, what does it look like? It just looks like a one-dimensional line. It has length, but from that distance, it seems to have absolutely no thickness.
Exactly. But if you walk right up to it, your perspective completely changes. You suddenly notice a second dimension. There is a circular dimension wrapping around the tube. If you imagine a little ant walking on that hose, the ant can move forward and backward along the length, but it can also crawl around the hose in a circle.
So from far away, the circular dimension is invisible. But up close, it is a fully navigable space. Space itself works exactly the same way. String theory suggests that at every single point in our normal 3-dimensional world, there are 6 extra dimensions curled up.
Curled up incredibly tightly. We are talking about the Planck scale here. That is billions of times smaller than a single subatomic particle. If you zoom in past a cell, past an atom, past the nucleus, you eventually hit a scale where ordinary space blossoms into these tiny, incredibly complex, 6-dimensional geometric knots.
Physicists actually have a name for these shapes. They model them as Calabi-Yau spaces. When you look at computer-generated models of them, they look like twisted, multi-dimensional origami. They are beautiful, but they are so complex that they almost break your brain trying to look at them.
Which begs the question, why do physicists insist on making the math this complicated? Why do we need these origami knots of space? The answer lies in how string theory explains the fundamental building blocks of reality.
Right, because for a long time, the standard model of physics told us that the universe is made of point-like particles, little dots of matter. But string theory says, no, those aren't dots. They are tiny, vibrating loops of energy. We call them strings.
Think of it like a musical instrument. If you pluck a violin string in a certain way, it creates a specific note. If you change the vibration, you get a completely different note. A quantum string works the exact same way, but instead of creating musical notes, it creates particles. One specific vibration makes an electron. A different vibration pattern makes a quark or a photon.
That is such a poetic way to look at the universe. Everything is essentially a cosmic symphony. But here is where the 10 dimensions become absolutely mandatory. For the mathematics of these vibrations to actually work out without completely destroying the known laws of physics, the strings need room to move.
They need exactly 10 dimensions to vibrate in. If they only had our three spatial dimensions, the math falls apart. The universe wouldn't exist. The shape of those hidden Calabi-Yau spaces literally dictates how the strings are allowed to vibrate.
And that is a profound realization. If you change the geometric shape of those 6 hidden dimensions, you change the vibration of the strings. That means you change the mass of an electron. You change the strength of electricity. You change the very laws of physics.
It is a staggering thought. The specific microscopic geometry of those hidden dimensions is the only reason our universe is capable of supporting life. Different shapes would equal entirely different universes with completely alien laws of physics.
Which naturally leads to a fascinating, almost philosophical question. If these 6 hidden dimensions are sitting right there at every point in space, dictating the rules of reality, can information travel between their world and our 4-dimensional world? Are we completely isolated?
The short answer is that no normal signal can cross over. In many modern string theory models, our visible universe is described as a structure called a brane. You can think of it like a flat, multidimensional sheet floating in a much larger space.
So we are essentially trapped on this brane. And all the forces we use to communicate, like electromagnetism, light waves, radio waves, they are physically glued to this brane. They cannot leak out into the higher dimensions. And nothing from the higher dimensions can leak in through those channels.
That is why we can't just point a radio telescope at the 6th dimension and listen for static. But there is one giant, glaring exception to this rule: gravity.
Gravity is such a weird force when you really think about it. Physicists have spent decades wondering why gravity is so incredibly weak compared to the other fundamental forces.
It really is absurdly weak. Think about a tiny refrigerator magnet. That little piece of metal can hold up a postcard, completely defying the gravitational pull of the entire planet Earth. An entire planet's mass is losing a tug-of-war to a magnet the size of a coin. Why?
String theory offers a brilliant explanation for this. It suggests that gravity isn't actually weak at all, it just appears weak to us because it is leaking.
Exactly. Unlike light or electromagnetism, the particle that is theorized to carry gravity, the graviton, is a closed loop of string. Because it is a closed loop, it isn't tethered to our brain. It isn't trapped in our 4-dimensional slice of reality. It can propagate and ripple through all 10 dimensions.
So when we experience gravity, we are only feeling the tiny fraction of it that happens to intersect with our brain. The rest of it is bleeding out into the hidden geometry of the universe. That makes gravity the ultimate theoretical bridge. It carries faint, indirect information about the geometry of those extra dimensions right into our world.
It completely shifts how we have to think about information exchange. When we usually think about communicating, we imagine sending a text message or beaming a radio signal across space. But higher dimensions don't talk to us like that. They don't send messages. They project structure.
And to really grasp how this structural projection works, we need to look at 3 profound principles of informational flow that govern this 10-dimensional universe. Let's call them the HD force, the B force, and the R force.
Let's start with the HD force, which stands for the higher dimension force. You can think of this as the ultimate cosmic projection engine.
The best way to visualize this is to imagine a 3-dimensional object, like a complex geometric crystal being held up in front of a light. It casts a 2-dimensional shadow onto a flat wall. Now, that flat shadow isn't receiving radio signals from the crystal. The shadow is just a compressed projection of the object.
And the shadow cannot escape the structure of the object casting it. That is exactly what the HD force does. It compresses higher dimensional information and projects it down into our 4-dimensional universe. It decides which physical laws survive the compression process.
It is incredibly humbling when you think about it. The fundamental constants of our universe, the exact speed of light, the precise mass of a proton, the exact strength of the nuclear forces, they aren't just random numbers. They are the shadows cast by those microscopic six-dimensional shapes. We are literally living in the shadow of a higher reality.
It feels very much like Plato's allegory of the cave, but played out on a quantum mechanical level. We are looking at the shadows on the wall and calling it the absolute truth, completely unaware of the massive, complex structures casting those shadows.
But a universe built on quantum projections is inherently chaotic. Which brings us to the second principle, the B force, or the balancing force. If the HD force decides what is mathematically possible, the B force decides what is actually stable.
Instability is a massive problem in quantum physics. Those hidden dimensions generate massive quantum fluctuations. They produce immense amounts of theoretical energy. If that energy was left unchecked, our universe would instantly explode outward or collapse back in on itself in a fraction of a second.
To understand the B force, think of a massive mixing desk in a professional recording studio. You have dozens of audio tracks. Some are incredibly loud, some are quiet, some have harsh frequencies. If you just push all the sliders up, you get a wall of unbearable noise. But a skilled audio engineer carefully adjusts the sliders, balancing massive opposing energy spikes perfectly, so the final song sounds beautiful and coherent.
The B-force is that cosmic audio engineer. It balances these massive, violently opposing quantum influences, keeping our universe in a perfect sweet spot. It ensures that vacuum energy remains stable enough for galaxies to form, for stars to ignite, and for us to sit here having this conversation without reality tearing itself apart.
It is a delicate, razor-thin balance. But even with perfect balance, things degrade over time. The universe is subject to entropy. Things get messy. Information gets scrambled. That brings us to the final piece of the puzzle, the R force, or the retrieving force.
This is the ultimate question of persistence. How does the intricate structure of the universe survive chaos, entropy, and the relentless passage of time? Why hasn't the universe forgotten its own laws after 14 billion years?
Think of a corrupted digital image file on your computer. Sometimes parts of the data get scrambled or missing, but a highly advanced restoration algorithm can look at the surrounding pixels, analyze the remaining data, and reconstruct the missing pieces until the picture is perfectly clear again.
It is a process of retrieval. It isn't time travel. It is structural restoration. The R-force ensures that even when information in our four-dimensional world becomes chaotic or scrambled, the underlying particles retain their quantum correlations.
It is like a cosmic backup system. It prevents the universe from forgetting its fundamental structure, ensuring that those higher dimensional laws remain completely coherent across billions of years and billions of light years of space.
So when we ask if there is an information exchange between the hidden dimensions and us, the answer is yes, but not in any way we intuitively understand. It is a continuous, seamless, and silent flow. It goes from structure to balance to recovery.
The extra dimensions don't talk to us. They build the arena we are allowed to play in. They are the invisible authors of the laws of physics, writing the code of reality from a microscopic realm we can't even see.
And while we can't see them right now, we are getting closer. As we build more powerful particle accelerators, and as we look deeper into the cosmos using gravitational wave detectors, we are hunting for those tiny leaks. We might one day catch a direct, measurable glimpse of these hidden folds in space.
It really makes you look at the world differently. Every time you drop an object and watch it fall, you are witnessing gravity leaking across 10 dimensions. Until our technology catches up to our mathematics, we are left to live our lives in the shadow of a grand 10-dimensional masterpiece.
It is a deeply philosophical place to leave it. We are a localized, four-dimensional expression of a much larger geometry. It makes the ordinary world seem entirely extraordinary.
Absolutely. It changes the way you look at a simple coffee mug on a table. If this mind-bending look into the true nature of reality clicked for you, take a moment to really think about it. Do you believe we will ever build the technology to find definitive proof of these hidden dimensions? It is a question that might define the next century of physics. We will keep exploring the edges of what is known, and we will see you next time.